This episode of Business Breakdowns is brought to you by Brex. Brex began as a corporate card for startups, but now offers an all-in-one solution to help you scale your business. Brex combines high-limit credit cards, spend controls, and accounting integrations into one platform. Brex is simplifying the process for founders and CFOs and quickly becoming the centralized tool for startup scaling. Just go to brex.com/businessbreakdowns to get a corporate card with 10 to 20 times higher limits, rewards, built-in expense software, and no personal guarantee required. Brex business accounts let you send free wires anywhere and make easy deposits. Start now at brex.com/businessbreakdowns and get up to 50,000 reward points. This episode is brought to you by MIT Investment Management Company, also known as MITIMCo. As the endowment office of MIT, MITIMCo searches for investment firms that are focused on achieving exceptional long-term investment returns. MITIMCo's goal is to create long-term relationships. They will partner with firms as early as day one and do not ask for general partner economics in return. Visit MITIMCo's website to learn more about their unconventional emerging manager approach, including examples of managers they have backed. While they only partner with a handful of new firms each year, they have also created and published resources for the broader universe of emerging managers to benefit from, making them even more unusual in the LP world. MITIMCo also opportunistically hires new members for their investment team. The MITIMCo team spends their time learning about great businesses and investments, working with exceptional investors around the world in order to support generations of MIT innovators. Visit mitimco.org, mitimco.org, to learn more. Click Join to learn more about the global investor role on MITIMCo's team, and click Emerging Managers to learn more about their emerging manager activities.
This is Business Breakdowns. Business Breakdowns is a series of conversations with investors and operators diving deep into a single business. For each business, we explore its history, its business model, its competitive advantages, and what makes it tick. We believe every business has lessons and secrets that investors and operators can learn from, and we are here to bring them to you. To find more episodes of Breakdowns, check out joincolossus.com. All opinions expressed by hosts and podcast guests are solely their own opinions. Hosts and podcast guests may maintain positions in the securities discussed in this podcast. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions.
Today, we're breaking down Novocure, a global oncology company that has pioneered a new approach to cancer treatment. For over 100 years, the tools used to fight cancer have largely remained unchanged, but there are promising signs of a renaissance, and Novocure is at the vanguard of that charge. To explain the state of cancer research and how the business has developed over the past 20 years, I'm joined by Bill Doyle, Novocure's executive chairman. Please enjoy this fantastic breakdown of Novocure. So, Bill, where to begin this really interesting conversation? It's a field that I have limited experience with, but a deep interest in. And before we get into Novocure specifically, maybe the best place to begin is a little bit higher level with just the state of cancer research and treatment writ large. You could sort of paint a picture for us of what the world looks like today relative to maybe when you first got involved in this space so that we can appreciate the rate of change and the state of the art today.
From my perspective, and I certainly don't have the only perspective here, but I think first and foremost, we're all familiar with cancer. We're all touched by it, either personally or through loved ones. I think we all fear it. We fear it because notwithstanding all of the research and progress that's been made, the approaches to treat chemotherapy haven't changed all that much in 100 years. We still have essentially three tools, and I'll expand upon this a little bit, but those three tools are well known: surgery, radiation therapy, and chemotherapy, or I'll make a slightly larger basket, pharmacological therapy. There have been progress made in all of those areas. They're all 120 years old, approximately, if you trace back to the first surgeries for breast cancer at Johns Hopkins, or the first chemotherapies that were used in Germany, and clearly the Curies in radiation therapy. We've got about 120 years of history, but still today, the majority, and really the vast majority of people who are diagnosed with cancer will die of that cancer. Now, we have some wonderful examples of some cures, great progress in areas, leukemia, certain types of breast cancer. But again, I can make the statement that most of the people who are diagnosed with cancer will die, in fact, of that cancer. Now, there is more than hope. There's been incredible, tremendous progress, particularly over the last 20 years. I think our understanding of the cell, understanding of the genetics of cells and proteins has clearly expanded, and that has led and is leading to new therapies. Today, it's still most effective of cancers, so-called the simpler cancers, the cancers that may result from a simple genetic mutation. And the more complex cancers, we've yet to make progress, but we think that progress may be very much on the horizon.
Could you just describe, maybe an overly simplistic question, but what cancer is literally? What is happening in the cells or in the body when somebody gets and has a cancer that grows and becomes life-threatening?
Of course, normal cells grow, they divide, and they die, and then are removed from the body. In its simplest sense, cancer is an uncontrolled growth that, in the case of solid tumors, which are the cancers that we're focused on, literally results in masses that impinge upon normally functioning organs, for the most part, and disrupt their function. Furthermore, those cancers will metastasize, and that's the fancy word for spread from their point of initiation to other parts of the body, creating satellite cancers that also have this deleterious effect.
And ultimately, when someone dies from a cancer, it is usually because that mass is strangling some critical function of the body. Like, why is uncontrolled growth so bad? How does this actually manifest downstream?
The obvious case where we're focused, which is in brain cancer, we're not getting scanned annually for brain cancer. So patients are diagnosed when a mass grows to a point where it impinges on a part of the brain and interrupts the function. So patients will have physiological symptoms. All of a sudden, they'll lose their vision, or they'll lose the power of speech, or very often they'll have a seizure, an uncontrolled seizure. Ultimately, they will die from the neurodegeneration that is caused by the growth of that tumor.
And if you think about the ways that we've had, the 120-year-old ways of addressing this problem, what are they primarily doing? Surgery is kind of obvious, you're taking it out. But what are the other two literally doing? And I think it's important to understand these other three before we get into what Novocure has innovated on and pursued since its founding.
So the first two are the simplest. As you mentioned, surgery is, in many respects, the most effective treatment that we have. And that's why there's such a push for early diagnosis. When a cancer can be diagnosed at a point when it hasn't spread and it's identified within a part of the body that can be removed, then the prognosis for those patients is excellent. Hence, things like colonoscopy for early diagnosis of colon cancer. If you can catch it in the very early stages, it's not really much of a problem. If you don't, it's a death sentence. Back to brain cancer, of course, can't remove the brain. So when cancers have either spread to a point where surgery is not practical, or they're in a part of the body where the function is critical and can't be removed, then surgery is not an option. So now we move to radiation therapy. Radiation can kill cells through the ionizing effect of the radiation. It turns out dividing cells are more sensitive to the effects of ionizing radiation than non-dividing cells. So back to what is cancer? Cancer is a rapidly dividing, uncontrolled group of cells. And the idea with radiation is that if you can expose those rapidly dividing cells, they will preferentially die compared to the healthy cells. Of course, the issue here is the healthy cells are affected too, and that's why there is a limit to the dose of radiation that can be delivered, and why there are issues with toxicity and side effects. So again, ultimately, you could kill any cancer with radiation. The problem is everything that's around it, and so it is limited by dose. Pharmacology is a much broader category. Chemotherapy, and these are the drugs that we're most familiar with, are essentially poisons. And it's the same idea. Provide a poison into the body that will affect the rapidly dividing cells more than it will affect the healthy, non-dividing or slowly dividing cells. But back to the same issue, severe side effects that ultimately limit the dose of the chemotherapies that can be delivered, and hence there's almost always recurrence, and ultimately patients die of the cancer. Now, the new area, and there's a few in here, but writ large are in the same category of pharmacological approaches, are the immunotherapies. And the idea behind immunotherapy is it's very enticing. One of the issues with cancer, or one of the questions with cancer, is this is a mutated cell that doesn't belong. Why doesn't our immune system just eliminate these cancers the way they eliminate bacteria or viruses? And they do. Most of us, our immune system is working to eliminate many cancers or growths that would become cancers, but the cancer cells themselves have developed many biological tricks, if you will, to evade the immune system. And one of the real foci now of oncology research is to unmask those cancer cells so the immune system can do its job. And we have some examples of some great successes here. The standard of care in lung cancer, for instance, which is the most common diagnosed cancer in the US and the world, has moved from first-line chemotherapy to first-line immunotherapies. I think we're in early innings here too, because again, even in lung cancer, most patients don't respond to those immunotherapies. I say most, the majority don't respond, and most of those patients will still ultimately die of the cancers.
And what about this emerging, exciting, obviously, category of very targeted treatments like the mRNA treatments that we've seen that we've used to inoculate ourselves against COVID? Is there technology that is emergent and new that fueled those things that could be also applied to attacking and destroying cancers in a more targeted, efficient way than some of the methods you've talked about?
Absolutely. I mean, fundamentally, one of the reasons that cancer has been so elusive is that cancer cells are very much like normal cells. When you attack a bacteria is very different than a normal healthy cell. A virus is very different than a normal healthy cell. But a cancer cell is very similar to a healthy cell. And that's why, as I mentioned, we have at least historically had such an issue with toxicity. And these therapies were ultimately limited by their toxicity, not by their effective dose. As we learn more about biology and we're able to understand the real subtle differences between cancer cells and healthy cells, then absolutely we can target those specific differences and ultimately kill the cancer cells and not the normal healthy cells. Now, again, cancer cells are clever, like viruses and bacteria. They mutate, they change. In many cancers, I mentioned before, the simple cancers are the cancers where we've had the most success, cancers where there may be one mutation. If you take a cancer like glioblastoma, GBM, brain cancer, where we have spent much of our time, those tumors may be characterized by hundreds of mutations. You use a targeted therapy, you attack one of those mutations, and I'll just use some arbitrary numbers to illustrate the point. Let's say 20% of the cancer cells have that mutation that can be targeted. You kill those 20%, but then the 80% come in and they grow. And that is part of the complexity here, that many of these tumors are not just one target away from eradication. But that's not, again, to say there's not tremendous progress being made in strategies. And one of the things you'll hear, and it's also a theme of our therapy, is the notion of multiple modalities. In the case of our therapy, which we'll discuss, tumor treating fields, we use them with surgery, we use them with radiation, we use them with chemotherapy. And in a very exciting way, we're starting to use them with immunotherapies because the therapies work better together than they do as so-called monotherapy.
Before we get to the specific technology and the business in a little bit more detail, just to round out our sort of opening salvo of painting the picture of this whole space, two other questions for you. The first is around prevention and detection. So it seems like most of what we've discussed is once you know there's a problem, these are the ways that we can deal with it. Has there been similar innovation in, you said we don't get our brains scanned every year, like why not? What would be the natural end state of technology that would allow us to identify these things very early? Because my understanding from our first discussion was that something like pancreatic cancer is so deadly because it can grow. The exponential growth curve is so much steeper. It goes undetected for a long time and then gets very serious very quickly. Say just a little bit about how we've prevented this or detected this early in the past and how we might in the future.
Historically, as I mentioned, we've detected cancer only when the cancer has grown to a point where a symptom is created. And then it's, okay, you have cancer. Sometimes that could be a lump, something that's physically observable. More often, it's a sickness. And you mentioned pancreatic cancer. Pancreatic cancer, even today, goes undiagnosed, often for long periods of time, because the symptoms are the same as stress or ulcers or stomach ache. It often is a bit of detective work to find the source of the symptom. There are technologies here that are emerging, principally in blood-borne detection of cancers. And I think in the near term, it's likely that we'll be able to get a blood test that will screen for dozens of cancers. And that will start then the search for the cancer and the therapeutic options. Now, the issue with diagnostics is, and we've all learned this as we've been tested for COVID, is that there are very few absolutely perfect diagnostics. So we always talk about false negatives and false positives. For screening large populations, the techniques have to have a very low false negative and, in particular, false positive rates so that there's not a whole bunch of activity that's created around an erroneous result. But I think the blood tests that are coming offer great promise. And then the question becomes, okay, what do you do about it? I'll keep going back to brain cancer where we're working. You now have a blood test that says you have glioblastoma. It's a deadly cancer. You get an MRI, they can't see anything. You can't remove your brain. Do you get radiation, which has a neurocognitive effect? So there are some questions. In some areas, of course, women who may have a propensity for breast cancer, for instance, many undergo a prophylactic mastectomy. If you saw early breast cancer in one of these blood tests, then the path might be very clear. In other cancers, I think the therapeutic strategies have to really be considered as we have early detection. But it's at the end of the day, it's basically good news if we can find these things earlier.
And then finally, as we bridge into Novocure, just give us a sense of the scope of this from both a health and a business size globally each year. Like how many people are getting cancer? You mentioned most people that get cancer die from it. So what are some stats around that? And what is the business of cancer today, excluding Novocure, which we'll explore in more detail?
The numbers in the US are very well documented. I mentioned the number one cancer, which is lung cancer. That's about 200,000 cases each year. We're just finished a phase 3 trial in ovarian cancer. That's about 40,000 patients a year. GBM, which is where we have focused much of our work, is a relatively rare cancer at 15,000 patients per year. So the numbers in the millions, the low millions, but that's the annual incidence. And then, of course, these patients will survive over different periods of time to create the prevalent population, which is at any one period of time, there are millions of people with cancer in the US at any one time.
In terms of just the businesses that have sprouted up, whether it's hospital systems, specific companies to serve this very sad market, in this case, these millions of patients, what is the breakdown of kind of that world?
First and foremost, there's the providers. It's a word I don't love, but we use these days, which are the doctors and the nurses and their staffs. There are oncology departments in every hospital in the US. That is further subspecialized into oncology focused, usually regionally, but focused in the head, the chest, or the abdominal area. There's another subspecialty of radiation oncologists who specialize in delivering radiation therapy. And then there are the companies, both drug companies and medical device companies that make the equipment and the pharmaceuticals that are used by those providers.
Now we can finally get, with that great setup and great overview of the space itself, into the technology that you at Novocure have pioneered, this idea of tumor treating field. So introduce us first to the technology, and then we'll use that understanding to start to dive into the business itself too.
So we start where you started. Historically, the therapies available to the oncologists have been broadly surgery, radiation, and drug therapies. Just discussed that the drug therapies and the strategies are expanding from poisons to things like immune stimulators, but still in that realm of pharmacology. Novocure has developed a completely new modality, a fourth modality to fight cancer. The original invention was made by a gentleman named Yoram Palti. Dr. Palti is an MD, PhD professor at the Technion in Israel. And Dr. Palti's expertise, actually his many expertise, but his principal expertise is the effect of electrical phenomenon on tissue. He was one of the pioneers in developing the technology that is used to treat, for instance, cardiac arrhythmias. When there are electrical signals that are going to the wrong place in the heart, that results in atria or the ventricles beating too quickly or too slowly. One of the therapeutic approaches to treat those arrhythmias is to map those electrical pathways that are firing in the wrong direction and then put a catheter inside the heart and make a small burn to prevent that pathway. Dr. Palti was at the forefront of developing those systems that are used in hospitals around the world. But about 20 years ago, he called me, and I got to know him in an earlier part of my career. I was responsible for R&D and business development in the medical device group at J&J. So I got to know Professor Palti as we were working on these cardiac ablation systems together. And he called me and I flew to Israel. We had lunch at one of these delightful beach restaurants in Tel Aviv. And I was expecting to hear the next generation of cardiac therapy. And he surprised me, an idea to treat cancer. And again, this was completely out of left field. But his idea was that many of the proteins that are involved in cell division have a very strong electrical charge. They're so-called strong dipoles. So they have a strong negative charge on one end of the protein and a positive charge on the other end of the protein. And electric fields, similar to magnetic fields or a gravitational field, a gravitational field pulls on masses, a magnetic field pulls on ferrous metals, an electrical field pulls on charged bodies. And he said, if I can get an electric field inside a cell, I think I can push and pull on those proteins. And instead of getting a normal cell division, I think I can kill that cell. And that was the fundamental idea that we now call tumor treating fields, that we can get an electric field selectively now into a rapidly dividing cancer cell, push and pull on the machinery of division, and instead of that cell dividing and becoming two cancer cells, have it die during cell division.
So going back to the issue that you brought up, cancer's difference from a bacteria or a virus that are so different. We've got cells that are roughly similar to normal healthy cells. What is the mechanism by which, I want to come back to how this thing actually works, the pulverizer of cancer cells through electrical fields, but how do you first make sure that you're not pulverizing good healthy cells? What is the difference that you're able to work off of to make this targeted?
That was one of the big questions on day one. This sounds good, but other cancer therapies, one, does it work? And two, what's the toxicity profile of this therapy? Because we were all brought up worried about our cell phones, worried about living under power lines. There's sort of all this mythology around electric fields. Now we're going to put it into the body. We have some lucky biology here. What I just described, in order for that to happen, obviously the electric field has to get into the cell. And it turns out the cell membrane that surrounds the cytoplasm is actually a pretty good filter for electric fields. It keeps the electric fields out of the cells. And in order to get the electric fields into the cell, we have to tune them to a specific frequency that will penetrate the cell membrane. And it turns out, because of a number of physical properties, back to the difference between cancer cells and normal cells, there are enough differences having to do with the salt on the membrane, the thickness of the membrane, the size of the membrane, where we can differentiate between cancer cells and normal dividing cells. The analogy I like to use here when I'm describing this to my non-physicist friends, which are most of my friends, we all have car radios. You can think about all the radio stations that we listen to all exist in the ether. It's not as if you're pressing a button and you're turning on one station. They're all there. But the box that we use allows us to filter one at a time. In the old days, when I had my first car, it had a knob, and I would turn that knob, which turned a capacitor. And I grew up outside of Baltimore, so I would go to 98 megahertz. That would let 98 rock into the amplifier, and that's what I would hear. If I get tired of that, I'd go to DC 101, 101 megahertz, and that would let 101 megahertz into the amplifier, and that's what I would hear. That's what we're doing with cells. We tune that frequency for GBM. The tumor treating fields get into the GBM cells. We want to treat pancreatic cancer. We tune the tumor treating fields to get into the pancreatic cancer, and then we treat that cancer. So it's maybe not a perfect analogy, but it's like tuning an FM radio.
What is the actual procedure? Is it a device? Is it something that you ingest? How do the fields get administered literally? Totally fascinating.
They are administered. And it's interesting, when we talk about the company, we really are a company like no other, in the sense that we're kind of a hybrid between a biotech and a medtech company. So all the clinical trials that we do are just like biotech trials in cancer. They're long, large, randomized phase 3 trials. The data that we publish is published in journals, in the same journals where drug trials are published. Rather than delivering our therapy in a bag that's infused into the body, we deliver our therapy through a medical device. So the patients carry around a box. The first box was the size of the stereo that I had in college. I have one of those luggage carts to move it around. Our first commercial device was smaller. It would go in a backpack, but was still a couple of kilograms. Our current device weighs about 1 kilogram and can go in a belt or a purse or a backpack. And like all things electric, it'll continue to get smaller. The biggest part of our system is the battery pack. We use the same cells that are used in the Tesla, for instance. So as the automotive industry improves batteries and battery technology, we benefit from that, and it keeps getting smaller. The box then is attached to the second component, which are patches. They're basically bandages. They're really antennae that are stuck to the skin in the area of the tumor. So if it's a brain tumor, the patient does shave his or her head and stick the patches left, right, front, and back on the head. If it's a lung cancer, again, it would be front, back, side to side on the torso. And that delivers the energy, the tumor treating fields, to the entire region of the cancer. This is another reason that we've shown such effectiveness, is that we're not, unlike radiation, a lot of the advances in radiation have come from pinpointing, getting the dose closer and closer to just the cancer cells, again, to avoid side effects. Because we have no toxicity, because we're only targeting the cancer cells, we can treat the entire region of the cancer, help prevent spread, treat cells that may have spread. And we can also treat for very long periods of time. So in the case of GBM, again, radiation, there's a maximum dose. Once you have 60 gray is the unit, you can't have any more because of toxicity. That's typically delivered over an 8-week period for most cancers. Our patients can receive therapy for years. So if there are stem cells, for instance, that are dormant for months or years, and then they, if you will, come to life, these patients can be receiving therapy to treat those downstream potential recurrences.
I'm completely fascinated by the technology, and I'd love to understand, you mentioned the pack itself is getting smaller. I'd like to understand the other lines that are improving, the other dimensions of this that you expect to get better through time because of technology. But before we do that, and then get into how many people this affects, et cetera, I'd love to just understand the results. You mentioned that you're treated the same way as, a pill or something that somebody takes in phase 3 randomized controlled trials. So just give us a sense of the impact, the number of cases that this is treated, what it does, actual results themselves.
So the first cancer that we focused on, and did this for a couple of reasons, not least of which it was the cancer that the FDA wanted us to focus on, was the deadly brain cancer, glioblastoma, or GBM. I mentioned before, GBM affects about 15,000 patients a year in the US. The median age is somewhere in the late 50s. It affects some patients who are much younger and some who are much older, but it's not primarily a geriatric cancer. It's a cancer that can affect patients in the prime. I like to think the 50s at this point are the prime of life. It's essentially a death sentence. It's now over 35 phase 3 trials of drugs have all failed in this disease. And there are a number of reasons for that. I think one, because it's in the head, which is protected by the blood-brain barrier. Two, we're limited to what we can do from a surgical perspective, obviously because it's the brain. Also limited to what we can do from a radiation perspective because it's the brain. And as I also mentioned earlier, it's a highly mutated tumor. It's not just one simple mutation. It can be hundreds of different mutations. The historic treatment is surgery. First of all, the patients will present, is the word. They'll show up when they have one of these symptoms that we talked about, a seizure or some loss of neurological function. Cancer is diagnosed with an MRI of a mass and then confirmed with a biopsy. Patients will receive maximum debulking surgery. Surgery is never curative in the case of GBM. It's just to alleviate those symptoms that are caused by the bulk of the tumor pushing up against a part of the brain that's causing the symptoms. Then they get as much radiation as they can give. This is balanced with these neurocognitive decline as a result of radiation, particularly in patients on the older side. And in many cases, they can't receive any radiation because of the quality of life issues. And then they receive an old chemotherapy called temozolomide or TMZ, which has been shown to bring the life expectancy of patients, actually have the exact data. And we think about this a couple of different ways. But in our trial, the control group who received the therapy I just described had a 5-year survival of about 5%.
Literally a death sentence, yeah.
Essentially no chance of 5-year survival. When we applied tumor treating fields after radiation with the TMZ, we increased the 5-year survival from 5% to about 13%. So we about tripled the 5-year survival, which is great on the face of it. But of course, that means there's still 85% of the patients who will demise before 5 years. I'll mention a couple of things. First of all, every patient who used the tumor treating fields lived longer than they would have without it. We show curves that show a separation at every point along the survival curve. The other thing that we saw, and this is driving our innovation, there is a pronounced dose response for tumor treating fields. What does that mean? In the simplest terms, it means tumor treating fields work when they're on and they don't work when they're not on. So one advantage to drug therapy is you get the infusion and then it's in your system. You don't have to do anything. You have to maybe suffer the side effects, but the patient doesn't have to do anything. In our case, the patient does have to change the battery and make sure that the therapy is on. Now, they do take breaks for showers and exercise. For those patients who use the therapy over 20 hours a day, so really used it, that 5-year survival went up to 30%. So now 5 to 30. So it's sort of a dramatic improvement. And you haven't asked the question yet, but why isn't that 80? Our belief is it's not 80 because we still don't have the dose as high as we would like. And we're doing a lot of things on the engineering side now to further improve the dose. In our preclinical work in animal models, we can kill all these tumors. We just need to get the dose higher. And so that's the future direction of the therapy.
This might be a crazy question. Is there a world in which I go a couple times a year as just a healthy person and just get like a prophylactic preventative dose of tumor treating fields? Like, is it toxicity and the side effects negligent enough that the extreme version of this is that everyone gets this as a sort of like kill 'em while they're young type therapy?
I wouldn't see everybody doing this, but now let's say you're a woman with a predisposition to breast cancer. One option is a prophylactic mastectomy. Another option could be, in that case, to use the tumor treating fields device while you sleep a few times a month or a week a month, which might be a better alternative. We talked earlier about the progress that's being made in blood-borne diagnostics. Now, let's say you have GBM in your blood stick. Now, I think, yes, absolutely, you would have tumor treating fields. In that case, it's probably not strictly prophylactic, but to prevent it from ever manifesting. So I think the world in which we have early diagnostics is a world where tumor treating fields, again, it's not just used randomly, but it can be used to prevent and fight these very early tumors when they're discovered.
This might be another odd question, but prior to meeting you, why had I not heard of this? I've known people that have had GBM for sure, obviously cancer writ large, and I was very familiar with the original three: surgery, radiation, chemotherapy. This didn't come out last year. Like, technology's been around for, I think, almost 20 years now. What are the interesting, non-obvious barriers to adoption? What do people fear about this? What are some of the non-medical challenges that you've faced? Why hadn't I heard of it?
Being a pioneer creates great opportunity. But also, there's huge challenges. I sort of joke when I had that lunch with Palti. The good news is I was trained as an engineer, so I knew what an electric field was. The bad news for me is I had no idea how hard it was going to be to change how medicine is practiced. I mean, let's face it, surgery, radiation, chemo, as I said, they've all been around for over 100 years. The current generation of oncologists studied these modalities in medical school. I won't call it the military industrial complex. The oncology industrial complex is focused around doing drug research. Most of the oncologists, there was always that point in, I don't know whether it's in high school or college, where you go to physics or biology. Vast majority of docs went biology. They didn't go to physics. So, a lot of my discussions with clinicians, and brilliant clinicians, but they start with, this is an electric field, really is physics 101. I think too, if you diagnose with GBM, I would hope, in the US at least, tumor treating fields would be presented to you as a therapy option. I know that's not universally the case yet. We're working very hard to make that the case. Right now, about 40% of the eligible patients in the US receive a prescription for tumor treating fields. Now, that's better than 5. The other 60 can all benefit. So we're working very hard to overcome those, really the educational gap. But, let's face it, I was skeptical when I first heard about this. Everybody starts skeptical, oh yeah, we're going to zap it with magic
rays.
Magic rays. From day one, we've focused on the science. The data that I just quoted were published in JAMA, one of the top couple of journals. So we're rated as a NCCN, that's the National Comprehensive Cancer Network, Category 1, which is a standard of care indication. But I think it's the burden of being a pioneer. And the next generation of oncologists will have studied it in medical school. And our next step is a company. So we're commercial. We have FDA approval. We're approved in Europe. We're approved in Japan. We're approved in China for GBM. Our next step is to complete a clinical trial program in the more prevalent cancers. So we have a stage 3 trial that's near completion of enrollment in non-small cell lung cancer. We have a stage 3 trial that just completed in ovarian cancer. We're recruiting a stage 3 trial in pancreatic cancer. And we just created partnerships, one with Merck in non-small cell lung cancer and a second with Roche, Genentech in pancreatic cancer. So these activities, I think, the news gets out and they're more discussed, I think will expand the universe of folks who have heard of us.
We've gone delightfully far in a conversation of this type where usually within the first 5 minutes, I've talked about the financial statements of the business. And in this case, it just doesn't seem like the right place to begin. And so I'm glad that we didn't. But I'm fascinated by how the business itself works. It's a big business, 500 million or so of revenues, lots of R&D, which obviously makes a ton of sense. Fairly high gross margins from what I can tell, near 80%. It has some of these features of the most fascinating businesses, which is fairly high gross margins, tons of R&D and innovation. So just talk me through the business of the business a little bit, like how you think about it in terms of its financials and the opportunity that it represents going forward.
I came out of, call it big med tech world, and had an opportunity to learn a lot about the good aspects from the business perspective and those aspects that are more challenging. And we tried to bring those to bear when we created the business around tumor treating fields. Again, as pioneers, because there was never a therapy like this before, there was never a business model either. And again, that's challenging, but it gave us an opportunity. So just as we have innovated on the therapy side, we've also innovated on the business model. Typical medical devices are either selling equipment, so they're box businesses. And from a business perspective, those are usually the least valuable because once a hospital owns a box, they try and keep the box as long as possible. This is the GE medical business. You try and build a service around it. You try and do a maintenance But at the end of the day, not all that interesting. The second business model is something that's implanted. This is the orthopedics industry. That can be a very good business because those are high quality differentiated products. This is cardiac stents, cardiac pacemakers. But at the end of the day, there too, most of those businesses, when the IP expires, there's competition. And this is what we want as consumers, of course. There's competition, price pressure. We still need very high quality. This stuff is not free, but there's a lot of pressure on margins. The third medtech business model is the disposable model. And, businesses bend over backwards, make their stuff, so you throw it away and you have to get another one. There's often good reasons for this, things that touch blood, things that are used in an OR, things that have to be sterilized. But the idea there, same thing, is disposable, and the pressure there comes on the cost of the disposable. I don't like any of those business models particularly for a number of reasons, but the customer ends up not being the patient. The customer ends up being a hospital or a doctor practice, most of which are either extremely price sensitive or broke. And there's all sorts of barriers. So the model that I wanted was a model that was much more drug-like. We provide a result that is as good or better as the best chemotherapies. Why shouldn't we receive value that's as good as the best chemotherapies? We also had kind of a unique situation where the patient is involved in the therapy, has to be trained, has to be monitored. So our model is essentially a subscription model. If you want to use the tech world, we receive a prescription from a oncologist. Then we send a technician to the patient's house. We bring the equipment, again, the 1 kilogram box and the batteries and the arrays. We train the patient, which means our customer is actually the patient here. We make sure that they're well trained. We make sure that they can use the equipment. We give them 24/7 support. If there's ever an issue, they don't have to try and get the doctor on the phone, which is good for us. It's also good for the doctor. The doctor doesn't want to get a call that a red light went on at 2 a.m.
On a device he's not an expert in, right?
Yeah, try and troubleshoot. Oops, the cat scratched the array or something like that. So we provide that 24/7 support. We refresh the arrays, the batteries, and we charge a monthly fee for the therapy. And the monthly fee works out to an amount that's very similar to what a patient would be charged for a high-end pharmacological therapy. But it means in our case, we bill the payer directly, we service the customer directly, and we don't have any middlemen who are, one, taking margin, or two, are somehow screwing things up, buying at the end of the quarter, or don't have room to store. I mean, from a patient perspective, and we received FDA approval for GBM in 2015. So about 6 years into the launch, we've never had a stock out. We've never not serviced a patient. That includes supply chain disruptions, COVID, natural disasters, hurricanes, and that's because we're doing it. If we were supplying into a distributor supply chain, I doubt we would be able to make that same statement.
I'd love to think a little bit about the future of value creation and value capture in the business. And on the value creation side, really that's about R&D and about, very simply, the new forms of cancer that you could treat, right? As the end goes up, obviously the economic opportunity goes up with it. You've already talked about that a little bit, but say a bit more about where the R&D dollars go and how much of it is horizontal, meaning new cancers, versus vertical, which would be better ways of delivery, new devices, new methods, whatever. How does the balance of R&D shake out in a business like this that will create all the value?
I mentioned before, we're sort of a hybrid of a biotech and a medtech. I actually think we're the best of both worlds. What do I mean by that? Really, we're not doing any R anymore. It's all D. So we're spending heavily to take the same mechanism of action, which we have in every cancer cell line we've tried, which is 20, 30 cell lines. Every animal model, every first in human has shown the same effect. We're now taking it from GBM, non-small cell lung, pancreatic, ovarian, brain metastases, liver, gastric. So it really is a clinical development program where the N is 20 to 30 times where we are today. So we have as you mentioned, about a 500 million plus business. We're really in US, Germany, and Japan. So one opportunity for growth is to spread into the other parts of the world, the rest of Europe. We're working on Canada, Australia, the rest of Asia Pacific. Further penetration. You mentioned we're about 40% in the US. I want to get the other 60%. We have to convince academics and skeptics, but those patients can all benefit. And then to spread into these much larger cancers. So non-small cell lung cancer, 200,000, pancreatic, 40,000, ovarian, ultimately breast, through development. So that's one. And then to improve the therapy. So with a drug, back to the biotech side, you have a great drug. These can be fabulous businesses. But the next breakthrough is the next drug. So it's back to the bench, back to discovery. In our case, again, best of both worlds, we're delivered by a technology that can get smaller, better, cheaper, and in our case, higher intensity. Today, our intensity or our dose is limited by the temperature on the skin. If you imagine, I've dragged you back to freshman physics, now back to freshman electrical engineering. You create heat where you have resistance. The most resistance is that interface between our arrays and the skin. That's where we create heat, which means our dose is limited by about 96 Fahrenheit. Once the arrays get at skin temperature, we can't go any higher. That's an engineering problem. That's a material science problem. And we're actually very far along with our next generation of arrays that will allow us to increase that dose significantly. We haven't yet mentioned the moats around this business, but one, I love the technology because we can help people and it's unique. Two, we've created a business model that I think improves on the business models of other medtech companies. Three, we have the opportunity just with organic growth to grow dramatically. And then four, we have great moats. Most medical technologies are really iterative. So, I was at J&J when the cardiac stents were developed. It was a huge breakthrough. Before cardiac stents, there were urological stents, there were biliary stents. So the patents were about features that were unique. They weren't about stents. So after J&J launched, it wasn't too long before Medtronic and Boston Scientific and Abbott were all in the business. And even though J&J was the pioneer, they were blown out of the water by these more nimble competitors. In our case, it's different. It's the rarer circumstance where Professor Palti really had the first brilliant insight. So we have over 180 patents globally, and they're fundamental. I talked about these improvements in the arrays, for instance. Every year, we're filing more patents on the improvements that we're making. Back to the biotech side of the business, you can't just make a box and an array and come into the market. From a regulatory perspective, a competitor would have to do their own phase 3 cancer trials. These are 2, 3, 4, 5-year trials, $100 million. So I think the regulatory barrier keeps the three guys in the garage out of the business. And I think the patents keep the established competitors who respect IP out of the business. So our moats are pretty good. And hence we have yet to see a competitor in our space.
You anticipated my value capture question perfectly, which leads me to one more question on the business, which is just the other sources of spending. So the revenue, as you've explained, and is straightforward. And it's also beautifully straightforward how that expands, both in market penetration, market expansion, and cancer expansion. That's kind of the equation of the business. What do you think about the rest of the way the business spends money? Is there sales and marketing that's important to talk about? Is there anything unique around G&A, the team that you put together and how you compensate them? Like just anything else to round out our clean here picture of the business itself would be great.
First and foremost, to be a global cancer company, a certain infrastructure is required. We have regulatory responsibilities. We have to interact with clinicians. We've built a substantial amount of that infrastructure globally based on our GBM business. So the GBM business has been a real privilege from a business perspective. We went public around the same time that we received FDA approval in 2015. We have not raised equity capital since going public. And for a biotech company, that's almost unheard of. Usually in biotech, the good news is we just had great results in a phase 3 trial. The bad news is now we need to raise another $1 billion to build a factory and build out the infrastructure. We don't have big factories. We leverage the global medtech supply chain. So this is a fairly capital light business, which might be non-intuitive, but it's capital light. We do spend on sales. We're not like a pacemaker or orthopedics where you almost need a sales rep in every operating room. The trauma cases were always, when I was working in the trauma industry, Unfortunately, there's a car accident, somebody comes in and you need your rep to say, use my stuff rather than the other rep saying, use my stuff. Our sales force is an education-based sales force, so we cover the US with about 50 reps. This is not the 300 or 400 rep, either drug sales force or orthopedic, say, sales force. Now, we will have to build a sales force for thoracic and a sales force for abdominal cancers. It will not be the same sales force that we use for the neurological cancers. They'll all be about the same size, these moderately sized. And then our big spend is in, I'll say D, not R&D, because we have this tremendous organic growth opportunity. Again, back to medtech. The big medtech companies are like Medtronic, Boston Scientific. They're constantly buying startups with new products. If you look at, they have billions of dollars of sales, but it's made up of thousands of SKUs in different areas, all sorts of issues associated with that growth model. We have organic growth. Our growth is organic growth opportunity from the same mechanism of action in different cancers. So ultimately, I think we get to a medtech-like P&L. We're not doing discovery research, so it's not going to be the 20, 25% that you see in biotech. It's going to be the 5, 6, 7% that you see in medtech.
If I had to keep it balanced, the smartest investor out there that did not like this story, even say someone that's short the stock or something like this, what do you think they would say? Like, what would be their reasoning behind not agreeing with the size and scope and probability of Novocure continuing the expansion that we've talked about today?
Now, over 20 years, I've heard you brought great data in the dish and it won't work in mice, and doctors won't use it. Oh, you can't get paid for it. All these things, we've heard them all. And for the most part, we've overcome everything. I think that investors today, I think the bears are more arguing about the ultimate potential here and the timing of the potential. Like other companies, we have had issues recruiting patients in the COVID environment in our clinical trials. Some have recruited faster than we would have expected. So the ovarian cancer trial recruited more quickly, but others have taken longer because patients are not coming into the hospitals. Their new centers are slowing their opening of the trial. So I would say the bears are more focused on the timing of the expansion rather than the expansion itself.
This is such a unique company story, and one that obviously it's hard innovation, it's science, it's a completely new modality. What broader business lessons would you share that you've learned in the experience of building this company? You're sitting down with your family or something and trying to impart the key lessons from this unique company building story. What stands out most in your mind?
First of all, this has not been an overnight success. It's 21 years in the making, and in many respects, we're really just getting started. So I would say this real transformational innovation, in particular in healthcare, does not happen quickly. Number one. Number two, it's felt like we've been pushing a rock up a hill. I have to be careful. Sometimes I get defensive, answering these questions. Not so much anymore, but some of that's just reflexive after 20 years of trying to explain what an electric field is and how we can help patients. But I think the lesson here is that people are not going to embrace something new just because it's interesting. Healthcare, we all like to think embraces innovation, but it's actually a very conservative. And when you add the hospital systems, the clinicians, the payers, the whole healthcare industrial complex, it's a very slow moving machine. And you have to really be prepared to fight for a long time on behalf of patients, but fight for a long time to make it work. Two other lessons. This is not an uncommon lesson, but I've been privileged to work with some exceptional people. My partner, but he's CEO, I'm the executive chairman, but we really essentially divide and conquer. The leadership is a gentleman named Asaf Danziger. He and I have worked together for 20 years. Without a real partner and a great team that's focused on the same things, I would say this would have been impossible. And the final thing I'll say from the business perspective, financing is critical. People come to me with all sorts of business plans in healthcare and whatever they call the series, whether it's Series A or Series 0. These types of innovations take a lot of investment. We raised approximately $500 million before we were able to break even and then go on our own steam. So I think, and again, in that first breakfast with Palti, I probably thought, okay, 20 million, not even close. The day that I saw our GBM results, I've told this story a few times, but we have teams in a variety of places in the world. Asaf is based in Tel Aviv. I'm based at our site in New Hampshire. We very often meet in Switzerland. It's halfway. So I had flown into Geneva. He had come in the night before. I was on the overnight plane. We go to this one little hotel, literally an inn outside of Geneva. And Asaf was standing in the parking lot with one piece of paper on it that said, "We won," which was the phase 3 results. And there are some moments like that make the more difficult challenges worth it at the end.
Well, it's an absolutely incredible story. I'm so thankful that I got to learn about the business through our mutual friend, Carl, got to meet you. I would love just kind of in closing, just to hear you riff a bit about the future of healthcare more generally. I mean, you've worked incredibly hard in one very specific area. It does seem to me from the cheap seats that we're in a renaissance of sorts, that for all sorts of reasons, technological and otherwise, we're making lots of advances. I think your caution that these things take a long time and a lot of capital is a really helpful and important one. It's actually very helpful to me looking at some companies in this space as an investor more recently. But just stepping back with your unique lens, what do you think about the future of healthcare? Have we entered what seems to be a new golden age or renaissance of this work and research? What has you most excited, and how do you also keep that view grounded?
I believe absolutely. I don't know, again, what the perfect analogy is, but I think where physics was in the 30s may not be a bad analogy to where we are, call it biology today. And the understandings that were developed in the 30s that led essentially to the electronics era in which we find ourselves today, the invention of the transistor being one of the pivotal moments, but from there, the development of integrated circuits and all of the computation that has been enabled really from this fundamental physics, again, that we can trace back to the 20s and 30s. Are we in the 20s, the 30s, the 40s? I'm not quite sure, but I think we are in that area. I have a great privilege of working with a brilliant engineer here in New Hampshire, Dean Kamen, and many of your listeners may know Dean. He's a very close friend, and we've been collaborating since the 90s. Dean's founded an institute that he calls ARMI, ARMI, the Advanced Regenerative Manufacturing Institute. And the notion here is that all these brilliant discoveries that are occurring in universities and labs, one petri dish at a time, if we actually want to treat tens of thousands, hundreds of thousands of patients, we can't expand it to hundreds of thousands of petri dishes. We need to come up with the fabs, if you will. But his vision, and I think it's real, is that we're treating heart disease, we're treating diabetes, we're treating cancers. It may not be too far when you have heart disease. Okay, well, here's a new heart. You have pancreatic disease, and it will seem barbaric that we were treating these sick organs, pushing them to the limit when we can just print one up and slap in a new one. So there's a lot that has to happen around that. But I actually think that is much of the future of the really expensive chronic diseases will be treated in that direction, along with really the fundamental understandings of what is going on in cells that are not behaving the way they should be.
Well, this, Bill, is such a unique conversation for me, not a topic area that I'm usually comfortable and certainly don't know a whole lot about, but I feel like I've just learned a tremendous amount from our few conversations. I'm so appreciative of your time and of all the work that you and your colleagues have done on Novocure. Thank you.
Well, it's my pleasure to meet you too.
To find more episodes of breakdowns ranging from Costco to Visa to Moderna, or to sign up for our weekly summary, check out joincolossus.com. That's JOINCOLOSSUS.com.